welcome to complex analysis, and this is the last session on the main results of holomorphic functions. Today we are going to prove three results which I would consider as loose ends, but they are very important for theoretical purpose, at least the first and the third. The first one is the Weierstrass theorem on uniform convergence of holomorphic functions, and second thing is the one which characterizes the connectivity or connectedness of the open set U in terms of the algebraic structure, namely the ring structure of the set of holomorphic functions on U. And the third thing talks about if F is a nowhere vanishing holomorphic function on an open set which is star shaped, then there exists G, a holomorphic function, such that e power G, that is exponential of G, equal to F. We call G as the logarithm of F. Okay, there is a holomorphic logarithm for F. Okay, these are the main results. All these results are easy. Okay, let's see whether I could do it in about 45-50 minutes. Okay, so the first result is the Weierstrass theorem. Okay, what does it say? Suppose U is open, and let us hereafter I will write H of U to be the set of holomorphic functions on U. Okay, this set is non-empty because constant functions are there, and because of algebra of differentiability, you know this is actually a vector space, complex vector space. Okay, and it also has a ring structure multiplication, that is F and G are there. Okay, I can define Fg is again holomorphic, which is defined to be F of Z into G of Z. Okay, since the constant function 1 is there, therefore H of U becomes an algebra, okay, which is essentially vector space structure as well as ring structure. Okay, in particular it's a commutative ring, with identity. Okay, so let us keep the notation. So let us prove the first result. Okay, suppose I have holomorphic functions Fn and okay, and there is a function F from U to C, so that Fn, if I know if Fn converges to F, okay, uniformly on compact subsets. Of U. Okay, yeah, it may not converge uniformly on the entire domain U, but only on compact subsets of U. In this connection, okay, as I think I already mentioned once, in complex analysis, uniform convergence on the entire domain is never required, but we will require only on compact subsets, because let us quickly recall, if F is a power series, okay, whose disk of convergence positive, okay, VAR, then if I look at Sn of Z to be the partial sum 0 to n Ck Z minus a to the power k, then Sn converges uniformly to F on any open disk of this kind, right? It does not converge uniformly on all of BA or the entire disk of convergence, but on subdisk. From this, it's very easy to show it to Sn converge to F uniformly on compact subsets of the disk of convergence BA capital R. Okay, okay, you just use the compactness, but you will see an occasion here. So usually one says this, okay, this is a definition. In that case, one says Fn converges to F locally uniformly. Okay, so what is the definition of F1 converges to F locally uniformly? F1 converges to F uniformly on each and every compact subset, okay, of U. Is that clear? Okay, then what is that I want to claim? I want to claim two things. One, okay, F is holomorphic, and since F is holomorphic, now I can talk about its derivative. So let us look at the kth derivative of Fn. Okay, okay, this converges to kth derivative of F locally uniformly. Okay, this is the kth derivative. So not only is the statement clear, what does it mean? The moment I know F1 converges to F locally uniformly, I know F is holomorphic, therefore it's infinitely differentiable. Therefore I can talk about this kth derivative of F. Then the kth derivative sequence F and K that converges to the kth derivative of F locally uniformly is something fantastic result. Okay, so let us go through a proof. Okay, the first one we had already seen as an application of Weierstrass theorem. Okay, first notice that F is continuous. Why? So fix any A in U and an R so that BAR is contained in U, right? Then let's look at 0 less than or less than capital R. Then let's look at F1 converge to F on the closed ball BAR, right? Because this is a BAR is a compact set, therefore this converges uniformly. Now F's are continuous, it converges uniformly to F, therefore I know F is continuous. Where? On BAR, right? In particular F is continuous at A. And this is true for all A, and therefore F is continuous on U. Okay, pause, review, proceed. Okay, now I can use Weierstrass theorem to prove F is. Recall what does Weierstrass theorem say? If I have F which is continuous function on U, okay, and F belong to H of U, okay, it gives a sufficient condition. Okay, if for every triangle delta contained in U and the path interval for the boundary of the triangle is 0, then F is holomorphic in U. This is what Weierstrass theorem says, right? So I want to use it. Now let's look at. Okay, now see I want to say F is holomorphic, right? So let us go slow. So you fix F. What do I want? I want to show F is holomorphic. Therefore, I have to start with a triangle delta contained in U and T with a boundary, right? Then what do I know of integral of F over T, right? Remember, I want to show F is holomorphic on U. Therefore, for any A in U, again I look at BAR as a layer, and therefore let's look at a delta contained in triangle. Okay, right? Now this is a star shaped domain, right? And by Cauchy's theorem, since F1s are holomorphic, this is 0. Okay, right? Now F1 converges to F uniformly on T because T is a compact set, right? Therefore, I know path integrals are behave well with it. Therefore, integral of Fn over the path T should converge to integral of F over the path P. But this is always 0. Therefore, I conclude integral of F over T is 0. Right? So, what I have shown, for every triangle delta contained in the disk BAR, which in turn is contained in U, okay, and this I have proved integral I over t is 0. Therefore, by Weierstrass theorem, I know f is holomorphic on where? On delta. Right? You understand that? Holomorphic at least on the interior of delta. Okay. So sorry, f is holomorphic on VAR. I'm sorry, I got carried away. This is more by Morera. Oh, okay. Because I have an open set and all of that over is 0. Okay. Then I don't. I concluded that. So if u is star shaped, if you want, you can assume that. Okay. Right. Is the proof clear? So this is the first proof. There is a second proof which will be more instructive, and that I need. So let us look at PR. So PRP. Okay. Now I will give a second proof. What is the second proof says? The second proof uses coefficient integral formula CIF. Okay. So I know f1 of z is going to be 1 by 2 pi I integral over gamma r f of f1 of w by w minus z dw. Okay, where 0 less than or less than capital R and gamma r of t. Okay, let us say simply gamma of t is a plus r e power I t, etc. Okay, I fixed a BAR containing u and a is new. Okay, all those things. Right? Okay. So now what do I know? Now, since Fn converges locally uniformly to F on gamma. Right? Now let's look at this is my gamma R, this is my A, my W is here and Z is here. Remember that now Z is fixed, right? Therefore 1 by W minus Z. So let us look at a picture so that you should understand what we are trying to say. Okay, my Z may be this. Okay, now look at all possible distances. Okay, since gamma is compact and Z is not on gamma, right? Modulus W minus Z is positive for all W in gamma, right? Now W going to mod W minus Z is a continuous function on the path gamma, and it's not 0, therefore it attains a minimum, right? Therefore there is a delta positive, so that mod W minus Z is greater than or equal to delta for every Z, for every W in gamma, right? Minimum, there is a minimum delta, okay, with this property, right? Therefore 1 upon W minus Z modulus is less than or equal to delta, right? Now let's look at, now again let us recall a standard result. If Fn converges to F uniformly on some set X and Gn converges to G uniformly on set, I cannot conclude Fn Gn converges to Fg uniformly. Okay, not true in general. But if I know Gn's are bounded, okay, uniformly, that is Gn is less than or equal to M for all n, then F and Gn converges to Fg, right? Now therefore, now come back to this. So I have my Fn, my G I can take to be 1 by W minus Z. If you want, I can also take Gn, but that is all the same. It does not depend upon Z. Therefore, Fn G converges to Fg uniformly on gamma. Okay, please understand this. Therefore, the path integral converges. What is the path integral? That is fn of w minus w minus z, okay, over gamma dw converges to integral of f of w by w minus z dw, right? But this is 1 by 2 pi I, and make it 1 by 2 pi I if you want, and but this fellow is nothing other than fn of z, yeah, and since but I know fn of fn converges locally uniformly, therefore it converges pointwise, therefore it should converge to f of z, right? But this fellow converges to this as well as this. By uniqueness of our limit, this f of z must be equal to this, right? Therefore therefore f is given by a Cauchy type integral, and hence it is analytic and holomorphic, and hence holomorphic in BAR, right? And this is true for all A, and hence I conclude true for all A in U, therefore conclude F is holomorphic on U. Okay, so this gives a second proof. So pause, review, proceed. Go through the proof once again. Okay, I was a little careful in explaining the things. Okay, instead of simply saying uniform convergence, I needed 1 by w minus z is also bounded. Therefore, I can conclude the uniform convergence of f1 by w minus z. Okay, right. Okay, now I want to prove the derivative, and now what is that I want to prove? I want to prove the kth derivative of this converges to kth derivative of this locally uniformly. Okay, and this proof is the second proof adapts to this, right? So how will I know? Say let the kth derivative of this is given by, I know this is equal to k factorial by 2 pi I integral over something. I will fix that in a minute, don't worry. F1 of w by w minus k to the power, sorry, w minus z to the power k plus 1 dw. Okay, now if you are given a in U, let me choose R such that BAR is contained in U. Let me choose R such that 0 less than 2R is less than capital R, right? Now my gamma of t is going to A plus 2R e power it, 0 less than or equal to t less than or equal to 2 pi. Okay, and the z I am going to take only in BAR. Okay, keep the picture in mind. So I have A, and this is my capital R, and this is my to R, and this is my R. My Z is going to be here. Okay, so the proof is exactly like earlier. What all I have to observe is, now let's look at W minus Z. Okay, so I have to use ML inequality, etc. So to do that, this time I am going to use ML inequality. In fact, last time I could have used ML inequality directly. Yeah, I could have done that, but I forgot. Okay, anyway, yeah. So now notice that W minus Z is greater than or equal to R. Why? Let us look at that. See, W is on 2R, right? Therefore, let us look at W minus A, that is 2R. Okay, that's less than or equal to W minus Z plus Z minus A. right? Therefore w minus z is greater than or equal to w minus a or 2r, but remember z is in bar, therefore minus mod z minus a, therefore that is greater than or equal to 2r minus r, which is r, right? Okay, therefore now I can estimate the path integral. Okay, 1 by 2 pi a etc. will be there. Let us just take it out, and there is a k factorial. Let me take it out. Now remember, since I by 1 I know f is holomorphic, therefore kth derivative of f is also given by quotient integral formula, right? Therefore I can write this as fn of w by w minus z to the power k plus 1, okay, minus f of w by w minus z to the power k plus 1. Okay, this is what I want to estimate. Therefore by ml, so what is the m? Therefore I have to look at f1 of w minus f of w. Notice that f1 converges to f uniformly on gamma. This is my gamma, where gamma is, as we did, gamma 2r, right? It converges uniformly. Therefore given epsilon positive, there is an n, so that for all w in gamma, mod f1 of w minus f of w will be less than or equal to epsilon. If you want, I can put a constant, let's not worry about, we will know what constant later. Okay, this is by because of local uniform convergence, right? That gives us. But now I know w minus z to the power k plus 1 is greater than or equal to, or 1 by 1 upon that is less than or equal to 1 by r to the power k plus 1. That's what we just saw because of this, right? Therefore my m is going to be, see, I have k factorial by 2 pi, the length is 2 pi 2r, therefore 2 times 2 pi r, and then epsilon by r to the power n plus 1. Do all of you understand that? Yeah, therefore f of f1 of w minus f of w by w minus z to the power k plus 1, that is less than or equal to epsilon by r to the power k plus 1. I wrote n, this is k. Do all of you understand? Yeah, so this is going to be 2 pi cancels, and 1 r cancels with this, therefore I have 2 k factorial by r to the power k into epsilon, right? So this is, that is mod f kth derivative of this z minus kth derivative of this is less than or equal to this. This is true for when, for all z in bar, right? Therefore f n k converges uniformly to the kth derivative on the open ball bar. So pause, review, proceed. Now suppose k is compact, right? Then for each a in k, I have some bar a, such that, of course, that is contained in u, and such that f kth derivative of n converges to kth derivative of this on bar a, right? Now the collection bar a as a varies over k is an open cover of k. Therefore by compactness there exists something like b a j r j, okay, 1 less than or equal to j less than or equal to some capital N, where r j is r of a j. This is a finite subcover, right? Now again, this is an easy fact. Suppose Fn converges to F uniformly on A and Fn converges to F uniformly on B, then Fn converges to F uniformly on A union B. Okay. For example, for this epsilon there will be n1, for this epsilon there will be n2. Take maximum of n1 and n2, then Fn will converge to F uniformly on A union B. Okay, these are all easy things. Okay, since my F, the kth derivative converges uniformly on this, on each and every B, A, J or J, for all J 1 less than equal to J less than equal to N, I concluded Fn kth derivative converges to this uniformly on the union. But K is a subset of this, right? Therefore, Fn converges to the kth derivative of Fn converges to kth derivative of F on the compact set. This is a very trivial compactness argument. All of you should know this. So go through this argument, the Weierstrass thing, okay, and both the arguments go through. Even in the first Mora thing, when I use Moreira, I could use ML inequality, okay, but in Moreira's theorem we used it also. But go through the proof, understand that, okay. But the arguments are very easy, very elementary arguments, but most often people will quickly write through argument, so I went through very slowly so that you can master how the analysis is done precisely. Okay, now we are going to prove the next result, characterization of connectivity through the algebraic structure of H of U. Yeah, let's do that. So let us go to the next result. So we want to prove the following theorem. This is actually an exercise in my book, if I remember right. Let U be open, okay, then U is connected if and only if H of U is an integral domain. Recall, if R is a commutative ring with identity, I say it's an integral domain if A B equal to 0 implies A is 0 or B is 0, right? So what is I have to prove? That means if I have F and G, okay, Fg belong to H of U, and we already defined Fg, this is a 0 function, then I have to prove either F is 0 or G is 0, right? Okay, the proof is extremely easy. It uses identity theorem. Okay, assume U is connected. Okay, and let Fg belong to U be such that F times G is 0. If F is not identically 0, then there is an A in U so that F of A is non-zero, right? And now remember, F is holomorphic, therefore F is continuous, right? Therefore there is an R positive so that, so this is my U and this is my A, and F of A, this is A, F of A is not 0, then I can find an R so that, okay, F is non-zero on BAR. So there is R positive so that for every Z in BAR which is contained in U, F of Z is non-zero. Yeah, this you know how to prove that. In case this is all the ordinary continuity, real analysis, topology, metric space, everything would have done. This is my FA, right? Choose an epsilon so that BFA epsilon avoids 0. Okay, it's away from 0. Then by continuity, I know there exists an open set containing, okay, you know UA, so that there exists by continuity of F at A, there exists an open set UA and with UA contained in U, so that f of UA is contained in B FA epsilon, right? Now since A is an open set containing UA is an open set containing A, there is an R such that BAR is contained in UA. Now if I take a Z, okay, then that f of Z will belong to f of UA, and hence it belong to this set, therefore f z is not equal to 0. Okay, this is a very elementary thing, because some of you may not have learned topology or analysis very well, so I am just explaining that if you are a good student, you should simply ignore this. Okay, right. So go back. If f of A is not equal to 0, there is an R positive, so that BAR is contained in U, and for all Z in BAR, f of Z is not equal to 0, right? But remember, BR is contained in U, and my fz and gz is 0 for all z in U. Therefore, it is 0 for all z in BAR, right? But f of z is not equal to 0 for all z in BAR. Therefore, what do I conclude? G of z is 0 for all z in BAR. Now, do you remember the easy corollary of identity theorem said, if I have a holomorphic function, recall, okay, easy corollary of identity theorem. What does it say? If I have f holomorphic function on U is connected, okay, and if f is 0 on a non-empty open set, okay, then f is identically 0. Therefore, this says G is 0 on U by identity theorem, or it's easy corollary if you want to. It's actually identity theorem because any open set, non-empty open set, every point is a cluster point. Therefore, the set of zeros of G has a cluster point. That's why it's actually identity theorem. Okay, please pause, review, proceed. The converse is easy. Okay, suppose H of U is an integral domain. I want to prove U is connected. Suppose not. Then I can write U equal to U1 union U2, so that U1 intersection U2 is empty, and U1 U2 are open, and U1 is not empty, and U2 is not empty. Right? Now define a function f of z equal to, let's say, 1 on U1 and 0 on U2, and define another function g of z which is 0 on U1 and 1 on U2. Notice that f and g are holomorphic because f is differentiable on U1, it's U is an open set, U1 is an open set with derivative 0, and f is differentiable on U2 with the derivative 0 because constant functions. This we had already seen when I talked about differentiability, right, where I proved if the derivative is 0, okay, then the function is locally constant. I cannot say it's a constant. Okay, it's a constant only if U is connected. Okay, at that point of time I had given an example similar to this. Okay, right? But what is f times g? Okay, either z, now z is suppose in U1, okay, therefore f of z will be 0. If z is in U2, then if z is in U1, right, then g of z is 0, right, f of z into g of z, and this is 0. And if z is in U2, then f of z into g of z, and this is 0, right. Therefore, what I have shown is f of z, f times g, f g is 0, but f is not 0 and g is not 0, a contradiction. Okay, so h of u is not an integral domain. Okay, so pause, review, proceed. Now we go to the third result. What is the third result? So let us, this is theorem. This is a very useful theorem. You will, okay, when you go for higher second course in complex analysis, etc., this result will be very often used. Even in our course, we may use it later, but at present I don't want to see. Suppose U is open and connected. Right? And suppose f is a function from U to C star holomorphic. That is, f is a holomorphic function U to C, such that f of z is different from 0 for all z in U. Okay? Then there exists a holomorphic function g from U to C, such that e power g is f. That is, f of z is exponential of g of z for all z in U. We usually call g a logarithm of f. Remember, we have seen a similar thing earlier where I proved if I have 1 by z, okay, in U, where U is a star shaped open set in C star, then logarithm exists. Okay, this I proved after Cauchy's theorem. So see, this is how you have to remember. See, you should not simply think you understand the proof, forget it. Now if I were you, what I will do is, after this watching this video, I'll go back to the video and look at the proof. Rather, if I'm confident, I will try to go through the proof. I already gave the hint. I used Cauchy's theorem, etc. Okay, Cauchy's theorem, Weierstrass theorem, etc. we are used to prove that. Anyway, go through it. Okay, now let's go through the proof. The proof, okay, uses the fact any holomorphic function is infinitely differentiable. Local primitive. Okay, on a star shaped domain, it has a primitive, right? Let us look at. Let me look at the function f dash by f. Okay. Now remember, f is holomorphic, therefore f dash is differentiable. Therefore f dash is holomorphic, and f is different from 0. Okay, f is not nowhere vanishing on the u, therefore 1 upon f is holomorphic. Therefore this is holomorphic on u. How many of you agree with that? Okay, right. Now this is a holomorphic thing on u, but u is open and star shaped. Okay, so any holomorphic function on an open star shaped set has a primitive. This we have seen, okay, in Cauchy's theorem. Therefore there exists a primitive phi of f dash by f. What does that mean? Phi dash is f dash by f. That there exists a holomorphic function, okay, so that phi dash equal to this. This is the meaning of primitive. Okay, pause, review, proceed. Okay, I hope all of you would go through the summary of Cauchy theory. Okay, it is better to kind of go through it at least twice or thrice so that you know this kind of thing I keep on using. Okay, you have gone through that as a theorem, check the proof, and you might have forgotten. You understood the proof, but forgotten. So that's not the correct thing. So you should review what are the major steps or milestones in Cauchy theory. That will help you to do this better. Okay, now let us look at e power minus phi times f. This is a function from u to c, and this is holomorphic. Why it's holomorphic? Okay, phi is holomorphic, therefore z going to minus phi z is holomorphic, that followed by exponential map that is holomorphic, composite of holomorphic function is holomorphic, f is holomorphic, product of holomorphic function is holomorphic, therefore this is holomorphic. So let me try to find the derivative. Okay, so I want to say the derivative, call this, if you want to call xi e power minus phi times phi, I want to say xi dash is 0. Okay, this is a claim. Let us check it. Okay, what is xi dash? Xi dash is the derivative of e power minus phi is e power minus phi, and the derivative of phi into f plus e power minus phi in the derivative of f, which is e power phi. So e power minus phi is common, and remember, go back here, phi dash equal to f dash into f, therefore phi dash f is f dash. Yeah, therefore this is minus f dash and plus e power minus phi into f dash, therefore this is 0. Alright, therefore xi is holomorphic function and u is star shaped, therefore it's connected, therefore that implies xi is a constant. Right, now xi is a constant. Let us look at what is xi. Psi of z is e power minus phi of z into f of z. Notice that this cannot be 0 for every z in u, right, because f of z for every z is non-zero and exponential is nowhere vanishing, therefore this is non-zero, right. Therefore if this is a constant psi of z, I can write it as something like r e power it, where r is positive, right, you understand. But this r itself I can write it as some e power s times e power it, right, r equal to e power s, that is this is e power s plus it, right. So let alpha equal to s plus it, then what is that I have done, e power minus phi times f is equal to e power alpha, therefore f equal to e power phi plus alpha, where phi is a function, alpha is a constant. So okay, therefore put g equal to phi plus alpha, therefore g is as desired. G is the desired function, so that e power g equal to f. Yeah, as an immediate corollary of this, okay, keep the same assumption, hypothesis of the last theorem. Then I want to say there exists a function, now I am running out of notation, okay, there is a function h which is holomorphic function on u, so that h squared equal to f, that is square root of any such function exists. That is very easy because I know f is e power g, right. So what I can take, okay, g by 2, okay, let you follow that. So let I do not know, notation is becoming difficult. Consider the function e power g by 2, okay, what is the square at any z by definition is e power g by 2 z into e power g of z by 2, that is e power g of z, which is f of z, right. Therefore this is the h I wanted, and this will be holomorphic because this is holomorphic, therefore e power g by 2, this is holomorphic, and whose square is f. So square root exists. So you all the three applications are very beautiful. Okay, if for nothing else, they allow you to make use of various results you have learned in Cauchy theory, like Cauchy's integral theorem, Weierstrass theorem, Cauchy integral formula, like that. Okay, so it's a very beautiful set of results. Please go through it and go through it, as I said, once or twice, and at many places I again recall or reviews in brief the earlier results. Okay, this is the way you have to learn all the time, so that you master the subject. It becomes part of you, as I said many times in the course, at many places. Now if you ask me something like, come on, 9 times 6, I know the answer. I don't know to go through the form multiplication table for 9 or multiplication table for 5, but the answer comes out quickly. Why? I keep on using it, reviewing it. Okay, the same thing. Please do that. You will enjoy mathematics. We will meet again.